This section is about matrix inverses, and it's one of the most important sections that we have. Why is that? Well, we've been talking about how to solve for the vector x in matrix equations like this one, where we have the matrix A multiplied by some unknown vector x, and the question is, what does the vector x need to be equal to so that the result is this vector on the right-hand side? And we've been doing this by row reducing the augmented matrix A augmented with the vector B. And that's fine, that's great, but there's a key relationship that we want to talk about, right? And that's hey, what if we knew what the inverse operation was here? So let me just quickly say that we solve an equation like 3x equals 7. How? Well, we divide both sides by 3. But division is the inverse operation of multiplication. So the question becomes, hey, can we figure out what the multiplicative inverse of a matrix is so we can divide through? That's exactly what they're doing to get from the right hand to the left hand side in this equation down here. Is they're trying to multiply on the left side by A inverse. And note that I haven't really defined what A inverse is, other than the fact I would know that multiplying A inverse times A would give me the multiplicative identity, which is the identity matrix. So it would be nice if we could figure out what A inverse was. And notice that you would also, I've multiplied by A inverse on the left-hand side, so I'd also need to multiply by inverse on the right-hand side. And notice that matrix multiplication is not necessarily commutative. So if I did a left multiplication on the left-hand side, I also have to do a left multiplication on the right-hand side. So the order of multiplication on the right-hand side is very important. And as a matter of fact, it's probably not even true. The if and only if statement is not even true if I do the multiplication the other way, which might not even be possible in many cases. So that's the point. We're going to define what it means to have an inverse matrix, and then we'll be able to use it like this to solve matrix equations. But then there's a huge batch of relationships which will be covered in the next section, section 3.6, which is the invertible matrix theorem. Once we know a matrix is invertible, we know it has lots of interesting properties. So the definition of an invertible matrix is right here. This is the key property. I need A to be a square matrix. That will become clear as you start calculating them using row reduction. But suppose we have a square matrix, then we're looking for a matrix B that has the property that when I multiply AB or when I multiply BA, I get the identity matrix. And now you can see why we need a square matrix, right? Because if A is a rectangular matrix, then I might be able to find a matrix B that made this true, but there's no, but even if I could multiply A and B, even if I could do this matrix multiplication, it would have a different size identity matrix, right? So if A was 2, 4, was a 2 by 4, then B would have to be a 4 by 2, and this one would be a 2 by 2, right? And then if I switch the order, I have a 4 by 2 times a 2 by 4, and so this would be the matrix I4, right? So it would be a 4 by 4. So that's why we have to have the square matrix. Let me get rid of some of those scratches. And you see that we're looking for a matrix B so that when I do the multiplication in either order, I get the identity matrix of size n, right? So if I start with a 4 by 4 matrix A, then when I'm looking for a matrix B that's also 4 by 4, that will, when I multiply it, either left multiply or right multiply times A, I get the I4 identity matrix. If I can find something like that, then we're going to call it the inverse matrix of A. A couple quick facts we will find useful going forward. The first is that the inverse of the inverse is just the matrix A. And if the product matrix A times B is invertible, then then its inverse, look at how you calculate its inverse. A times B inverse is B inverse times A inverse. All right. So notice they say note the order. This is the shoes and socks principle that when I do, this is also true of matrix transformation, excuse me, transpositions, right? When I take the transpose of a matrix, it's also in the reverse order. But so A times B inverse is B inverse times A inverse. And again, remember that matrix multiplication is not necessarily commutative, so this order is going to be very important. We need to cover one final thing before we start defining in general how a process for calculating the inverse matrix. And the fact is that we're going to define the determinant of a 2 by 2 matrix. Now, like most matrix things, the calculation of higher order determinant is a nested process where to find the determinant of a 6 by 6, I take the determinant of a bunch of 5 by 5 matrices, and to find each of those 5 by 5 matrix determinants, I work with 4 by 4s and then 3 by 3s, and I finally get down to 2 by 2. But this is the base one. At its very core, I need to understand how to calculate what the definition of the determinant is in the 2 by 2 case. And notice that it's just the difference of the main diagonal entries, A times D, minus the off diagonal entries, B times C. So the determinant of any 2 by 2 matrix is just AD minus BC. And let's take a look at why this is true. One way to see if it's true is just to start with an example, right? And check to see if I calculate using this formula, whether or not I have the inverse matrix. So notice this, where I'll just point this out, that to find the inverse matrix, we have, I'm sorry, I went past the formula. Here's the formula for the inverse of a matrix, and you'll see why we calculate or defined the determinant of A, because if I have this general matrix A, B, C, D, what do? Well, along the main diagonal, I swap the two entries, right? A would be in the top left, D would be in the bottom right, and I swap them. And notice that along the off diagonal, the entries stay in the same position, but I take their opposites. And then if I do that to the matrix, then I find the rest of the inverse by multiplying by this real number, 1 over the determinant of A. Well, that's why we need to know what a 2 by 2 determinant is. That way we can calculate 2 by 2 inverses when they're possible, okay? And where I was right here, where the book shows an example. They're like, hey, if that formula is true, let's just do it to A and see if that produces a matrix like B, so that A times B equals the identity and B times A equals the identity. So look at what they're doing first. The first thing is to take the main diagonal and swap their positions. Okay, so the 1 goes to where the 4 was, the 4 goes to where the 1 was. On the off diagonal, everything becomes its opposite, right? So the positive 3 and positive 2 become negative 3 and negative 2. Then you multiply by the determinant of A. Well, what's the determinant of A? Well, it's the main diagonal entries multiply the product of the main diagonal entries, so 1 times 4, minus the off diagonal entries, which is 3 times 2. And so I have 4 minus 6, which equals 2, right? That's the, is negative 2. And that's where the negative and the 2 is coming from, right here. So they multiply this out, and actually they don't. They just leave the, because that would end up with generating some fractions in the bottom. So they just leave it. Then what are they doing here? Well, this is the original matrix A. It's being multiplied by its inverse, A inverse, and what's the result need to be? Well, if it actually works, which it does, then I get the identity matrix. So now we're ready to define a way to calculate inverse matrices, and it's going to, unsurprisingly, involve row reducing an augmented matrix. And what they're saying is, hey, I'm going to take, if I want to try to find A inverse, then I'm going to take the matrix A and I'm going to augment it with the identity matrix. Now remember, A must be a square matrix, must be n by n. So I know exactly what inverse matrix to, what identity matrix to augment it with. And then I row reduce it all the way to the form where I have some matrix on the right side of the augmentation bar and the identity matrix on the left. So this needs to go all the way to RREF. I can't stop at REF. I have to go all the way to reduced row echelon form. But when I do, the matrix that is left, or the matrix that remains on the right-hand side, is in fact A inverse. If I don't glitch somewhere, right? So I might do this row reducing and find an inconsistent matrix on the left. If I do, if it glitches somewhere like that and I end up with an inconsistent matrix on the left, then the matrix A doesn't have an inverse, right? A is not invertible. What we'd like to do here is we'd like to put this method to the test. So the idea is that we're going to take the matrix A to find the matrix inverse of A. I'm going to take the matrix A, and I'm going to augment it with the identity matrix. Now A is a 3 by 3, so the identity matrix that I want is the 3 by 3 identity matrix. And the process is to find the REF of this matrix, which I'm going to do using row operations, at least for the first one. So I'm going to work out the row operations now. So let me do the augmentation. As usual, pro tip, always use lowercase letters to do your row operations because it's much more efficient. And so I'm going to create an augmented matrix, little a, that is A augmented with the identity matrix of size 3 by 3. And there we go. So you see that I have it. Matlab unfortunately won't put in the augmentation bar, but you see that if I put one in, I have the identity matrix here on the right. So to row reduce, the first thing I need to do is get zeros below that top left one. So I've made a fairly easy matrix here to row reduce. So I'm going to start in the second row, and the second row is just going to be the second row minus the first row. All right, and then I can copy paste because the third row is basically the same, except I'm going to subtract 2 times the first row. All right, and you can see that now I have zeros below the first pivot. So as usual, I'm going to throw in some semicolons to stop displaying some of the stuff up here, just to make this a little cleaner. These are the row reduction steps that I've done, and this is the place I've gotten to. So now I need to get a positive one here. So all I'm doing in this step is multiplying row 2 by -1. Let's see, so how about, row 2 is going to be row 2 times a -1. And now we have our second pivot. We need to get our third pivot in place. So we're going to take, we're going to get a 0 below the second pivot, row 3 is going to be 4 times row 2, So, right, row 3 equals row 3 plus 4 times row 2. That should give us a 0 below the second pivot, and there we go. We have our 0 below the second pivot now. All right. So now we have all of our pivots. This one just happened to be 1 at the end, so we're good. And we have zeros below all of our pivots. So our next step, this is REF, we'd be fine here, but the next step is to go to RREF. So remember, the process is to get zeros above all of my pivots now. So I start off getting zeros below my pivots, and I finish by starting on the right-hand side, moving back to the left, getting zeros above. So row 2, let me try, I can copy paste in. Let's see what we have. So that's rows 2 and 3. I need row 2 to just be added to row 3, or row 3 to be added to row 2, and the result to be put in there. And now I have my first zero above the last pivot there. And so I'm going to copy paste in again. Row 1 needs to be row 1 plus 2 times row 3. Let me scoot over so that the tooltips aren't in the way and double check this. Yes, if I take 2 times the third row and add it to the first, then I can replace that minus 2 with the result, which leaves a 1 above. So I've gotten my zeros above my first pivot, and I just need one more step to finish, to get all the way to RREF. Okay, so we've put in some semicolons, and now we're going to be ready to do this last step. So what do I need to do? I need to take row 1 equals row 1 minus 4 times row 2 to get that last pivot, right? So now, since we have the identity matrix on the left side of our augmented matrix, and we've done proper row reducing steps, not found any inconsistencies, the matrix that's on the right-hand side here is A inverse. And how would we check that? Well, we can multiply. Let's extract it first. So let's say that, let's just get this matrix M equals A. All right. So why did I do that? Well, because I want to pull this thing off. Let's see. So matrix M is going to be all the rows, but the only columns I want are columns 4, 5, and 6. Right? There we go. So I was just trying to pull off the right-hand side of the augmentation bar, which is columns 4, 5, and 6. Now I have a matrix A, and this is our candidate for A inverse. Okay, so let's try it. Let's multiply A times M, and we get the identity matrix. And let's multiply M times A, and we've checked both directions, and we can see that that M is in fact A inverse. And we have one other check we can do. We do have the inverse matrix operation in Matlab, so I can try inverse of A equal M, for example. And notice that I get a 1 in every position, which means that every single element in the inverse of A was equal to the corresponding element in the matrix M. I'm sorry, in the, yes, so every I'm having trouble speaking this morning. Let me ditch this, right? If I just were to do inverse of A, you'll see that each of the components matches what I calculated when I got M by doing row reduction. So the point of this section is that I can do I can find matrix inverses simply by row reducing. All right, and let's just finish this. We can get. So the final thing we want to do is look at a 4x4 matrix and just make sure we understand the process. So remember, I'm going to want the inverse function. Excuse me, I'm going to want. Well, let's do it this way. So we have the matrix B, and I can use the inverse function just to see what the inverse of B would be. And notice that if I multiply the inverse of b times b, I get the identity, although you can see there's some rounding error. And I can also do this in the reverse order, take b times the inverse of b, and that got pretty ugly. That's interesting. Um, but we know what the inverse matrix is, and we know what the inverse matrix is, and we also know that we can row reduce, right? So let me do the augmented matrix of B with the identity matrix. This is a 4x4, so I need the 4x4 identity. And now I can row reduce this augmented matrix. And the only point with this is that when I get this augmented matrix into RREF, then the thing that I have on the right side of the augmentation bar is in fact the inverse matrix that we calculated. For example, you can look at the fourth column, right? -7, -9, -1, and 8. So we're matching up either way we go. So what is the result? Well, now we have a method where we can use row reduction to find any matrix inverse, as long as we know what the 2x2 determinant means, right? That's one of the key things about figuring out what this all means. So in the final moments of the video, I want to show you using Matlab how we know that the inverse, how we know this formula for the inverse of a 2x2 matrix. So when we use this syms statement in Matlab, it's going to treat A, B, and C as variables. All right, so symbolic, S-I-M-S, or S-Y-M, sorry, sim, is for symbolic. Algebra. It's going to let us do row operations, and it's going to treat them as variables. So the first thing I have here, right, you'll notice, oh, this is nice, right? It's actually displaying this matrix A, B, C, D. And I can do row operations on it. And the first thing, so what I want to do is I want to actually create the augmented matrix, matrix M, augmented with the 2x2 identity, right? And then I want to calculate the inverse. Now that I have the identity matrix, the matrix M in terms of A, B, C, and D, I want to augment it with the identity matrix. And there you can see, so we have the matrix M on the left-hand side, we have the identity matrix on the right-hand side, and we need to row reduce. So the first thing that I need is I need A, the A is my pivot in the top left, and I need that to be 1. So I can simply multiply row 1 by 1 over A, or divide through by A. And you can see that when I'm in Sims mode here, it's doing this algebraically. So the next step that we need to complete here is to change the bottom left to a 0. So I need to multiply by the top, I need to replace the second row with the second row minus C over A times the first row. And the result looks a little bit ugly, all right, but it has done what we need it to do. And what's interesting to note is that I have in this numerator here, I have D minus BC. All right, so if I multiplied this thing through by A, well, if I had an A along with the D, I actually have the determinant starting to appear. So that's interesting and helpful. And now I need to get a 1 in this location, which can be done by multiplying through by 1 over what's in the red box. And it looks a little bit ugly, but I've put the d over a minus bc over a squared, and I'm just dividing through row 2. And so now look, the right-hand side, if I put in the augmentation bar, the right-hand side is ugly. But the left-hand side, we're nearly there, right? We just have a straightforward row operation to convert this to a 0. And I want you to focus on this right here, because think about this. If I have a squared times this value, which in a minute, as it gets complicated, the Matlab is going to start referring to this as sigma 1, the things that this value here that's in the parentheses is going to be sigma 1. But if I think about a squared times this value, if I distribute this, I'm going to cancel the a's here. I'm going to cancel one of the a's here, so I'll end up with the determinant. I'll end up with AD minus BC. Same thing will happen here. So a squared times sigma 1, what the Matlab is calling sigma 1, is actually the determinant of this original matrix. That's the determinant of what we were calling M, I guess. And so the final step is to get rid of that B over A. So we're just going to add minus B over A times row 2 and add that to row 1. And yes, the result is a little bit ugly, but notice what it's done. It's defined this sigma 1 as the stuff that's inside the parentheses, and now it's reporting the values here in terms of sigma 1. We'll leave the top left hand for just a minute, but remember that a squared times sigma 1 is just equal to the determinant of this original matrix. Okay, so I have minus b over the determinant of M. I have here, right? And I have my minus c over the determinant of M. And what's this equal to? Well, this, the bottom right-hand side, is equal to a over the determinant of M. Sorry, that's supposed to be a d. Over the determinant of M. Why? Well, think about this. If I have an a squared in the denominator, then a squared times sigma 1 is equal to the determinant of M. So I'm just multiplying through this bottom right. I'm just multiplying on top and bottom by an a. So if I multiply by a over a, I have an a squared on the bottom, and that's what produces the a in the numerator. Okay, so that's all fine and good. So we have everything we need, but except we need to show, need to understand why up here this value is equal to d over the determinant of M. Right? That should be d over the determinant of M. Well, what we're going to do to see this is if you factor out a 1 over, if you factor out a 1 over a out of that expression, right, I have 1 plus, and then I have my BC, and then I also have my a squared sigma 1 here. Okay, so if I factor out this 1 over a, right, and why did I do that? Well, I have exactly what I need on the right-hand side. I have BC over the determinant of M, right? And so when I get a common denominator, right, what will I end up with? Well, I'm going to end up with the determinant of M, right? So this is going to be, sorry, I need the 1 over a, right? So I have 1 over a times the determinant sorry, that's AD minus BC, AD minus BC, right? And then it's the A squared sigma 1 is just AD minus BC, and that's in the, we have a common denominator now, so AD minus BC in the denominator. And then I have, for the second fraction, I just have plus BC. Well, there you go. The minus BC and the plus BC cancel, and so I just end up with D over the determinant, AD minus BC, because the A here and the A here cancel. So what have we found? Well, we've just determined that this formula that we were shown in the book actually works. That in fact, when I do the matrix algebra, I do in fact get an A in the bottom right and a positive D in the top left, and that these off-diagonal entries switched position, did not switch positions, but changed signs, and every one of those was divided by the determinant of A, that AD minus BC value. So you can do it by hand and get the same things happening, but I thought it was kind of cool that we could show it happening in Matlab. So the upshot is we now know how to calculate the inverse matrix of any invertible matrix. We just do row operations on the augmented matrix until we find that it's inconsistent, which means it doesn't have an inverse, or we get all the way to RREF, which is the identity matrix on the left. And if we can get there, then whatever remains on the right is the inverse matrix.